Welcome to today's lecture. Today we will continue our discussion on cluster algebra from surfaces. So starting with a bordered surface, which is a Riemann surface with marked points, either on the boundary or as a puncture. Last time we talked about how we can associate to such a surface a triangulation, and from the triangulation we get a quiver, and from the quiver we define a cluster algebra of geometric type. So we give the identification of the cluster algebra complex and the exchange graph with the arc complex and dual graph of the triangulation of your surface. So a flip of the triangulation will correspond to a cluster mutation. Each arc of the triangulation will correspond to the cluster variables. So we have seen that there are some problems when you have self-folded triangle in your triangulations and you cannot flip the internal edge. So we resolve this by introducing an extended version of the triangulation called the tag triangulation. And with this, we successfully identify the arc complex with the cluster complex. So today we will talk about the geometric meaning of those cluster variables. And it turns out that this can be described as the coordinates called lambda lengths of some geometric object called the Teichmüller space of the surface. So recall that if you have a simply connected Riemann surface, so a Riemann surface that has no holes, the fundamental group is trivial, then it is known from the uniformization theorem by Poincaré that it is conformally equivalent to one of the three Riemann surfaces, either the Riemann sphere, the complex plane, or the open unit disk. And in particular, this means that every Riemann surface will admit a Riemannian metric of constant curvature. So if they are quotient of the Riemann sphere, then it has positive constant curvature. And if it is complex plane, like the torus, then quotient of complex plane, like the torus, then it can have a flat metric. And otherwise, if it is a quotient of the open unit disk, so it emits a hyperbolic structure, and the Riemann surface will have negative constant curvature. And all this will depend on the value of the Euler characteristic of your Riemannian surface. So in this lecture, we'll be interested in looking at the hyperbolic structures of your bordered surface, and this will be parameterized or encoded by the so-called Teichmüller space. So the Teichmüller space of a bordered surface, which I'll write as T of Sm. So this is the moduli space, which I'll explain, of hyperbolic structure with constant curvature -1 on the surface removing the mark points. And we require that the boundary components are geodesics. So the boundary removing the mark points will be some components of the boundary, and we require this to be also the geodesics, the curve of shortest length under this hyperbolic metric. And this is the moduli space. So we want to identify two such hyperbolic structure if they are related by diffeomorphisms of the surface fixing the mark point that are homotopic to the identity. So It turns out that a surface admits the constant curvature -1, so admits a hyperbolic metric if the other characteristic, the n that we talked about last time, is positive. So it means that it has at least one arc from the ideal triangulation. That's why we insist on having a positive number of arcs in the last lecture. So then this is a kind of a well-known object, and it is known that the Teichmüller space is actually a manifold of dimension n minus p. So n is the number of arcs we did last time, and you can again write down explicitly. So G will be the genus of your surface, B is the number of boundary components, P is the number of punctures, and C is the number of marked points on the boundary. So a corollary of the uniformization theorem also tells you that for 2D Riemannian surface, talking about hyperbolic structure, in other words, a Riemannian metric on the surface, is the same as describing a complex structures, or how one can patch your manifold using a holomorphic map between different coordinates. And this is again the same as saying talking about a conformal structures. So all the patching maps are conformal mappings. And this is true in 2D because we all know that holomorphic functions in 2D corresponds to conformal mapping of the complex plane. So so we have a surface and we want to describe its hyperbolic metric. So one way to do this, as we mentioned before, is to look at it in terms of a quotient of the hyperbolic unit disk, or equivalently as, say, a upper half plane, which admits a natural hyperbolic structure. So this is the Fuchs model, or you can say it's also a consequence of the uniformization theorem. Although here we have a little bit more general surface because we allow some marked points. So every bordered surface with hyperbolic structure can be described by a quotient of the upper half plane with a discrete group. So here H is the upper half plane model. So it's just the part in the complex plane with the positive imaginary points. So it admits a metric given by dx squared dy squared divided by y squared. So the boundary of the upper half plane model will just be the real line. So in particular, this will be the infinity of our model, because as you see, when the height, so y is the imaginary coordinate. So as y goes closer and closer to the real line, the metric gets bigger and bigger. So in fact, it goes to infinity. It directs to infinity when you approach the boundary. So this will be the infinity. And sometimes people will also take the union with the infinity point. So the gamma here will be the fundamental group of our bordered surface. And here we will treat M as punctures or points that are not in our surface. So what we really mean here is the fundamental group of S removing the map point. So this will act by deck transform. Because the upper half plane model is the universal cover of your surface, so for a loop on the surface will correspond to a curve on the upper half plane. And it turns out that this can be realized as Möbius transformation. So Möbius transformations are transformation on the upper half plane of this form where the ABCD belongs to PSL2R. Right, so this means that the fundamental group can be realized as a discrete subgroup of the PSL2R. And this discrete subgroup is known as Fission subgroup. So this is a realization of your surface. So instead, so I mean, if you look at the universal cover of your surface, it will be the upper half plane model, and then you can obtain your surface by quotienting out this upper half plane by the action of a discrete subgroup of PSL2R. So basically, you identify the orbits of the points on the upper half plane, and in particular, the hyperbolic metric of this upper half plane will descend to a hyperbolic metric on your surface with constant curvature -1. So usually people talk about the uniformization for surface without punctures. So if you have punctures in your surface, just like this more general case, then we also require that this gamma as a discrete subgroup of PSL2R also have the condition that the loop around punctures. So non-trivial loops around punctures will act by parabolic elements. So these are the group elements where the trace is either 2 or -2. Let's use G for the group. So if you have a non-trivial loop inside your fundamental group, then it will act by some matrix in PSL2R where the trace is ± 2. So this is one way to see the hyperbolic structure of a surface, but as we all know, there are also another model of the hyperbolic space known as the open unit disk model or the Poincare disk model. So here it turns out that this might be a more convenient setup for us. So we can consider a conformal transformation from our upper half plane to the Poincare disk. So the Poincare disk is just a unit disk of radius 1, open disk of radius 1. So here, this is the Cayley transform, mapping a point on the upper half plane to a point on the unit disk given by C minus complex number I over C plus complex number I. So in particular, this map will provide a hyperbolic metric on the unit disk given by the following formula. And also then the mark points in both cases will be lifted to the boundary. In other words, the infinity of the disk. And also GD6 will lift to the GD6 of on D, which will be the circular arcs in D. So these are the circular arcs that is perpendicular to the boundary. Yeah, so I mean, I should also write here that the marked points here will lift to the boundary, which is the real line. So all the marked points should lie on infinity. So just maybe you can look at an example. So this is a Riemann surface of genus 2 and with one puncture. So we know that such a surface can be realized just like the torus by identifying an octagon, identifying the size of an octagon. And so the red line here will correspond to the triangulation of this genus 2 surface. So the Poincare disk model of this surface will be the following on the unit disk. So it will have all the sides of the octagon becomes GD6 on the disk. So GD6 here again means that they should be circular arc such that it forms a 90-degree with the boundary. So these are all GD6 and it is a universal cover. So by the action of the fundamental group, it will extend beyond to infinity. So the boundary will be infinity. And so this new arc here will correspond to the other copy of your octagon, but shifted. So let's say if this side is identified with this side, then this side will identify with this side, and so on. Or maybe the other one. Anyway. Yeah. And so last time we talked about ideal triangulations. So in the polygon picture, it's just the usual triangles. But now we require that these red lines, the edge of the triangles, should also be GD6 on your Poincare disk model. So in particular, each triangle will have their vertex on infinity. Because remember, the triangulations are defined so that the arc starts and ends at mark points, and all our mark points are lying on the infinity. And in particular, this means that the length of the geodesics, the length of the edge of the triangles will all be infinite, as one can check using the hyperbolic metric. So a remark on the Teichmüller space is that it has another realization from the previous discussion. So it will be a moduli space of all the homomorphisms from your fundamental group to PSL to R, right? Because as we have seen in this picture or in this language, to describe a hyperbolic structure really is describing the embedding of your fundamental group into PSL to R. So this is equivalent. So this means that giving the image of the fundamental group in PSL to R will describe the hyperbolic structures. So here we then can say that the Teichmüller space will be the moduli space of the homomorphisms from the fundamental group to PSL to R modulo the action of the group on the image by conjugation. So this will act here by conjugations. So we quotient out by this action. And the prime here means that the homomorphisms has to be faithful because we want the fundamental group to be a subgroup of PSL to R. Into a fusion or discrete subgroup. Up to conjugation on the image. All right, so this is like this is the description of the definition of the Teichmüller space. So now we want to have a more concrete realization. So remember, we want to study the hyperbolic structure of the surface, but to describe a hyperbolic metric on your surface really is saying that giving a curve, I can know the length of the curve, or in other words, you can always describe the geodesics on the surface. So if you know the geodesics between 2 points, so the curve or the distance between 2 points, then it will uniquely define your hyperbolic structure. So to describe a hyperbolic structure on a surface, you really only need to describe the collection of geodesics. And this will naturally give you a coordinate system of your Teichmüller space. But as we mentioned here, we see that the geodesics of the triangulations are all have infinite length because the endpoints lie on infinity. So to remedy this, we would like to truncate the geodesics so that it becomes finite length. And this can be done by introducing the concept of Horror cycle. So a Horror cycle around a mark point, this will be a curve that is perpendicular to every geodesic starting from P. So we will define a slightly bigger space called a decorated Teichmüller space with a tilde. So this will be just the usual Teichmüller space together with the information of the Horo cycle around each puncture. So it is a collection, it is the Teichmüller space together with a collection of Horo cycles. And it turns out that these Horo cycles can be realized very nicely in the open unit disk model. So recall that in the open unit disk, all the marked points lies on the boundary. And then it turns out that the Horo cycles, the curve that is perpendicular to every geodesics, are just realized as circles tangent to P. So to be clear, let me just import a picture. Or I can actually see here already. Yeah, I should be using D instead. So in this picture, this will be a puncture, this will be another puncture, and the Horo cycles will be these circles. And you can see that this circle is perpendicular to every curve coming out from P, right? So the decorated Teichmüller space really is telling you the information of these circles, or you can say the radius of each circle. So different choice of radius will give you different choice of Horo cycles. So now to define the lambda length, which is already kind of in this picture. So we let gamma to be an ideal arc or a boundary segment, because we assume that the boundary components are also geodesics. So we can always choose the arc of the triangulation to be a geodesic naturally. Then we define the L length of the arc to be the signed hyperbolic distance between the Horo cycles at the endpoint of gamma. So what does this mean? So if you look at the picture above, then the red curve here will be a arc of the triangulation. Or if you look at this, then it will be a boundary segment. Really? Oh, well, I mean, in this case, probably not, because the surface has no boundary. But anyway, so we have a geodesic of your triangulation. Then we have a Horo cycle. And this Horo cycle will cut out a segment of your triangulations, of your arc. So the purple part here. Then we define L of gamma to be the hyperbolic distance of this purple arc. And now, because it is starting and ending at some interior point of your unit disk, it has finite length. And signed here means that if the configuration is like this picture, then you will have the positive number as your distance. But if your Horo cycle is too big so that they overlap, then we will take the negative of the distance. Then finally, the lambda length will be defined by e to the power L of gamma over 2. Alright, so what we have done so far is that first we start with a surface, then we look at the universal cover in terms of the open unit disk or the Poincare disk model. And from a triangulation of your surface, it will lead to a bunch of geodesics, the circular arc on this Poincare disk. So each arc will start and end at the boundary of your circle. Then for each puncture or for each marked point of your surface, which lies on the boundary, we choose a horocycle. So this means that we are supplying a bunch of positive real numbers describing the radius of such circle tangent to the puncture. Then for each arc, we look at the distance truncated by the horocycles, and this distance will be finite because both endpoints now lie in the interior, and we take the hyperbolic distance of this truncated arc and raise back to the exponential. So this data will be enough to determine uniquely your hyperbolic metric. So to define the hyperbolic metric, what you only need is to supply the information of the length of the triangulations, which depends on the choice of horocycles. So the theorem is the following. For each ideal triangulation, T of the marked surface, the map which sends the lambda, the collection of lambda links. So either it is an arc of the triangulation or a boundary segment. Then this will give a homomorphism of your decorated Teichmüller space. So this means that the lambda length will give you enough information of the decorated Teichmüller space. And this gives you a coordinate system of the decorated Teichmüller space. But naturally, the Teichmüller space is just obtained from the decorated one by forgetting the horocycles. So to obtain a coordinate system on the usual Teichmüller space, what we do is to take the cross ratio. So the coordinate can be obtained by taking the cross ratios. So it is the following. So let's say I have a configuration like this, and I have the arcs. So I should draw like curved, but I mean, you can always model the lifting of this picture. So in the decorated version, we define the lambda length by providing a choice of horocycle, cutting our arc. Then we will define the cross ratio to be the ratio of the lambda length, like this. So this lambda length will depend on the size of these horocycles, but it turns out that the cross ratio, chi here, will not depend on the choice. So indeed, it gives a well-defined coordinate on the usual Teichmüller space where we don't have the information of the Horner cycles. However, this Teichmüller space will be cut out by some linear relations. So these cross ratios are not independent of each other, unlike the decorated coordinate. So there exist linear relations among the cross ratio. So more precisely, if you have a marked point and then you have several arcs coming out from this mark point, so you have all the cross ratios associated to this edge, then we will require that the sum of all the cross ratio around a puncture to be 0. So the coordinates will not be independent. But in any case, the lambda length is a very nice simply connected space, just the quadrant of the real space for the decorated version, and you are kind of getting a non-trivial coordinates when you go to the usual Teichmüller space. So this is much more complicated object. All right, so now we would like to understand more about the lambda length, because we want to identify this with the cluster variables, and cluster variables, as we all know, has a mutation formula, and geometrically the mutation should look like the Ternary relations, and it turns out that this is the case. But to prove such result, it will be benefit for us to introduce yet another hyperbolic model. So this will be the hyperboloid model. So first we introduce a Minkowski space. So this is just a three-dimensional space, but we have the inner product given by the following formula. So U here will be XYZ. So this will be the sign to one inner product. Then the hyperbolic model, or the hyperboloid model, which I denote by H positive. This will be all the points on the Minkowski space with norm 1. And the positive here means that we also want the C coordinate of these points to be positive. So if you draw on the 3D space, this will be just the hyperboloid on the upper half space. And naturally, we can define the map from this hyperboloid back to the Poincare disk by stereographic projections. So the Poincare disk here will be realized as just the unique disk in our Minkowski space. So it is a standard stereographic projection. So given a point here, let's say U here, we maps to the point on the unit disk given by joining the point with the point 0, 0, -1 and intersecting on the xy plane. So you have a disk here. Then you have a 0, 0, 1 here. Then for a point here, you will join with the 0, 0, -1. The intersection will be the corresponding point. Yeah, so maybe it's better to just include a graphic here for a better look. Yeah, so this is plot from Mathematica. So the blue part here will be the hyperboloid. D will be the Poincare disk. And say if you have a point U, then you have the line joining U with, I mean the blue point. If a line joining the blue point with 0, 0, -1, the intersection will be this point here. So a well-known result is the following. So if you have 2 points on the hyperboloid, then the hyperbolic distance pulling back from the unique disk is given by the following. So it will just be defined as the hyperbolic distance on the Poincare disk, and this will satisfy the hypercosine of D equals the inner product of the 2 points. So it has a very simple formula. So given 2 points on the hyperboloid, we project it back down to the Poincare disk and look at the hyperbolic distance on the disk. And it turns out that this distance can be described just by the inner product of the points on the hyperboloid. So to describe the lambda length, we need to have horocycles, and it turns out also that this is very easy in terms of the Minkowski space. So first we define the positive light cone, L plus. So these are all the points on the Minkowski space such that it has 0 norm, again with positive height. So this term definitely comes from physics. It's like where how the light travel. So the negative signature will be the space and the positive signature will be the time, and light will be on the boundary of that, and blah, blah, blah. Then it turns out that a point on the light cone will uniquely define a horocycle. So this will be all the elements on your hyperboloid with inner product 1 with your point. So these are the horocycles. And finally, it turns out that the lambda length between 2 points is exactly given by just the inner product of the two. So lambda UV here means the lambda length between the horocycle. Sorry, I should not have read that. So let's look at the picture again. Oops, what happens? Yeah, so let's look at the picture again. So given a point, so now I have the green U. So given a point on the light cone, so U lies on the light cone, then we can define this set. So this set will be this parabola on H, and then the stereographic projection of this parabola will be exactly the horocycle you can see here. So if I have HU correspond to this circle here, and let's say I have another point V, and then another hyperboloid, and then it projects to this horizontal. Then we talk about the length between the two horizontals, so the second part here. So this will be our lambda UV. The length will be the lambda UV, and it turns out that the lambda length is just given by the inner product of this and this vector inside the Minkowski space. So it has a very nice description. Okay. So with this description of lambda length in terms of the inner product on the Minkowski space, then it turns out that the lambda length will satisfy Ternary relation, exactly the same as the classical case. And in fact, the proof also follows from the classical Ternary relations. So let me write down the proposition. So if you have 4 arc, or actually maybe 6 arc, so either arc or boundary segment in the following configuration. So now all of these are geodesics, but then you have a choice of horocycles. Then we have the Ternary relation given by exactly the same formula. So again, remember that this lambda length depends on the choice of the radius of these horocycles. But no matter what radius you start from, you still have this relation hold. So we see that this is a direct generalization of the classical Ternary relation, where you have embedded straight lines on a circle. But it turns out that the proof of this proposition is exactly it follows directly from the classical Ternary. So let's try to see how this is solved. So let's say we have the lambda length given by two horocycles given by ui and uj on the light cones, and say I is 1, 2, 3. Yeah, so instead of alpha, beta, gamma, I just use say 1, 2, 3, 4 to describe the punctures. So let's say we have the lambda length between ui and uj. Then the above Ternary relation rewritten is really just 1, 3, 1, 3, 2. So maybe I use 1. My alpha is 1, 2. So okay, maybe this. It doesn't really matter. All right. So if I rewrite the Ternary relation above, then I have lambda 1, 3, lambda 2, 4 equals lambda 1, 2, lambda 3, 4 plus lambda 1, 4, lambda 2, 3, right? So this is the same, but I just rewrite in terms of a better notation labeled by the punctures. But then you can see easily that this equation is invariant under rescaling each of the UIs. Because I mean each term has exactly one of the index. So say if you rescale U1, then this lambda length will get rescaled. This will get rescaled, this will get rescaled. So the relation does not change. So if we can rescale all the UIs, then we can rescale in such a way that they all have the same height. On the positive light cone. Right, so if you start from, so this is the light cone, if you start from 4 points corresponding to the 4 horocycles, then you can rescale them so that they all have the same height, and this means that they will lie on a Euclidean circle. So now all 4 points lie on the circle. Then we know that the Euclidean distance between them satisfies the Ternary relation. So this is the Euclidean distance between the rescaled vector. So this is given by the high school geometry. So if you rewrite y square, y square, x square, yj square, minus this, minus that. And using the fact that they lie on the light cone, you can see that this is given by this expression, which is nothing but the inner product, the Minkowski inner product, which by definition is distance squared, of course, which by definition is the lambda length squared. So since we know that the Euclidean distance satisfies the classical Ternary relation, then we conclude that the lambda length also satisfies the Ternary relation. So let me just write here. So Ternary for the classical Euclidean D will implies then the Ternary for the lambda length. Right. So we see that the lambda length really gives you a candidate for cluster variables because you have Ternary, so you can kind of do mutations just like before. But we have to check that the Ternary relation holds in all possible situations. So not just the standard quadrilateral, but we also need to consider the self-folded triangle case. And it turns out that there will be some problems sometimes. So let's look at first the good example. So let's say we have a sphere with 4 puncture. So this is a sphere with 4 puncture. So please try to imagine. So the white image is like wrapped around at the bottom, at the back. So it is a sphere, and then you have 4 points. And then you have this geodesics, which gives some triangles. So for example, I mean 1, 2, 3. So this is a triangle, right? And like 1, 2, 3. This is another triangle. So this is actually the configuration for a flip, and Ternary's relation holds pretty well in this case. So the following relations still hold. So now the beta is shared by 2 triangles, and you still have such a relation. So actually, as a corollary, if S has no puncture, then we don't have the self-folded triangles. Then everything is just the standard autonomy, and the lambda length already gives all the possible exchange relation. So this is already a good case. However, if the surface has puncture, so let's look at the bad cases. So if S has puncture and you have a configuration of the two-gon with a puncture like this, then there will be a problem with the digon flip. Right, so here we really have the standard digon flipping with the, the standard digon flipping with this arc here. And so if you just draw the conclusion from the Ternary relation, we see that the gamma will be shared by two triangles. So if you just write down the Ternary relations, which still holds, of course, because I mean this is geometric, so it still holds, but then you see the problem here that you have a common factor on the right hand side. But remember, for cluster algebra, you do not allow common factors in your mutation rule. So this cannot give you the exchange relations. So this problem arises from digon flip, and last time we resolved the case, and it also kind of implicitly telling you that you cannot mutate at this internal edge because of the formula. So last time we resolved this by introducing the tag triangulation. So here the tag triangulation then will correspond also to some kind of version of tagged lambda length. So to resolve this exchange relation problem, we just need to modify the definition of lambda lengths for tagged arcs. So instead of working with the standard triangulation, just like before, we should turn everything into the tagged version and introduce lambda length for the tag triangulation so that we have a good exchange relation. So to define this modified version, first we introduce the conjugated horocycle. So a conjugated horocycle, H bar, of a horocycle at a punctured point is just the horocycle such that the geodesic length, the product of the geodesic length is 1. Yeah, so the horocycle is a circle. So you can define the, it's the hyperbolic length of the horocycle. So it actually has a finite length. So we define the circle. So if the original circle is small, then the conjugated circle will be big and vice versa. So let's see the special case for a one-gon with one puncture. So in this case, so I'm drawing the horocycle on a surface. So in a surface, a horocycle is just a curve surrounding the puncture. So, yeah, so it has finite geodesic length. So if you have a horocycle H, then you also consider the conjugated horocycle, and you have another point Q with another horocycle truncating the arc at Q. Then the distance between P and Q, you now have two versions depending on which horocycle you choose. So it is denoted by P or P bar, and QQ is this length here. So it's the length cut out by the horocycle. Then in this configuration, we have the following formula. So it turns out that the lambda length of the outer boundary is just the same as the product of the two truncated arc between P and Q. So this is the bad situation in the classical case with one gone and one puncture. And remember, we resolved this by having a tagged arc. So now we can define lambda length of tagged arc using such an idea. So first of all, if gamma is an arc without any tagging, then the lambda length is just as usual, the old definition. However, if your arc is tagged, say at a puncture P, then we will use the conjugated horocycle at P instead of the original chosen horocycle to define gamma instead. So then it follows from the previous lemma that this gives a very good resolvent. So remember, we have this situation where, say, gamma is untagged and gamma prime is tagged, and we have eta here, and here gamma undone version, the untagged version are the same. So it has tagged the same at Q and different at P. Then from the previous lemma, we see that the lambda length of eta is just the product of the lambda length of gamma and lambda length of gamma prime. So of course, using our definition, the lambda for eta will use the horocycle Q or Q conjugate, depending on whether there's a tag at Q. Yeah, so with this tagging, which follows from this lemma, we can resolve this diagonal flip. So let's write down the conclusion. First of all, we have the Ternary relation. So this is just the standard relation for the tagged arc. Oops. So this is the example we have previously with the sphere with 4 punctures. Now we can write down the Ternary relations. So previously, remember, beta is shared. And now we will write them in terms of the tag arc instead of the puncture, instead of a loop inside puncture. Because remember, for tag triangulation, we do not allow such configuration, and instead we replace this by the tag arc. So this is the old triangulation, and now we are rewriting this in terms of the tag triangulation. But now we know that lambda of alpha is nothing but the original alpha is nothing but the product of alpha prime and alpha prime. And similarly, gamma, the original gamma is this, but now we don't want such curve here, and we replace by the tag version, and we know that this is gamma prime plus. So this will be the Ternary relation, the quadrilateral flip case. So instead of a loop with giving one gun with one puncture, we turn it into tag arc, and then the exchange relation becomes something like this. And then of course the troublesome diagon. Now it will be turned to this picture. So previously we have a loop going like this, and now we replace by the tag arc. So previously we have the eta going this way, but now we know that the lambda length of eta will be the product of gamma and gamma and gamma prime in this case, in this notation. So previously we have the Ternary relation, which remember is a bad relation because they have a common factor. So it cannot be an exchange relation. But now if we rewrite everything in terms of tag arc, so we do not allow eta, then this can be rewritten by removing the gamma, lambda gamma. So this will be the diagon relations in the tag arc version. And now this will be a nice candidate for mutations. Then everything just carries forwards. So now you have a formula that allows you to do mutations. All right, so to summarize everything, we write down the main theorem. So the lambda lengths for tagged arcs form a cluster exchange pattern. Or you can say that all the cluster variables are restrict to positive real numbers, positive real valued numbers. So in this cluster algebra, the coefficients semi-field will be generated by lambda of the boundary segment. And our ambient field will be generated over this semi-field by the lambda length of a given triangulation. The initial triangulation without any tag arc or without any self-folded triangles. Just like the previous lecture. The exchange graph is just the exchange graph of the tag triangulations. So seeds will be labeled by the vertex of the exchange graph. So each triangulation gives you a seed, and each cluster of a triangulation will consist of the lambda length of the tag arc of your triangulation. Exchange matrix is what we have done before. It's just a sign adjacency matrix. Of the undone version of your tag triangulation, or the exchange relation we have is then just given by the Ternary relation and the diagonal relation that we have described on the lambda length. And of course, finally, the exchange pattern does not depend on the choice of initial triangulation. So this is the general philosophy for cluster algebra. All right, so this kind of concludes the main feature of cluster algebra from surface. Of course, I missed some or quite a lot of details, so you should consult the paper by Fomin-Thurston on cluster algebra of surface 1 and 2 to check for more details and calculations. So we discussed the Teichmüller theory associated to surface, and it turns out that there is a natural generalization where instead of the PSL2R, the Möbius transform, we replace this PSL2R by arbitrary algebraic group or split semi-simple algebraic group, and this leads to a notion of Fock-and-Goncharov's higher Teichmüller theory, and also the notion of what's called the cluster A and cluster X variety. So next class, we will try very hard to discuss the definition, trying to skip all the important details because the paper is actually quite dense and long to read. So I try to summarize what I can. The meaning of cluster A and X variety, the higher Teichmüller theory, and how everything patched up together, which is kind of an active area of research right now. All right, so thanks for your attention. So I hope you stay for the last chapter on the course on higher Teichmüller theory next time.